Great. So I'm really excited to be speaking here. It's my first time speaking to an HCI audience of any kind, so I hope you'll forgive me if I don't follow the norms that need to be followed. So a couple comments on the work I'm going to talk about. It is sort of work that has a pretty strongly statistical nature, but I prepared the talk sort of from first principles. So we're going to give, the talk is actually in 3 parts. There's going to be sort of an introduction to kind of what we did, and then I'm going to go at the board, actually, which is an amazing thing. I hope that everybody can be OK with that. So I'm going to actually use the board to give you some intuition for why our idea works. And then I'll go back and show you some more slides on some of the results and visuals of the platform. So what is the talk about? The talk is actually about some work that I did with a platform called Optimizely. And so I want to be clear that this is work that I actually did as a technical advisor to Optimizely. So, in particular, just by way of full disclosure, I'm still an advisor to them, and this is work that I did essentially as a consultant for them. The idea was that we wanted to try to think about how people look at the information that you report after a randomized experiment called an A/B test in sort of technology platforms, and how do they process the information that they get back. Okay, so let's start by first just talking about what is A/B testing. So this is just to make sure that I set context for everyone. Hopefully those of you that have sort of been around the tech industry would have seen something like this before. But the idea is that A/B testing is, in Silicon Valley, we have to invent new names for old things all the time. So A/B testing is a new name for an old thing called a randomized controlled trial. Okay? And randomized controlled trials are sort of the gold standard of experimentation. The basic idea is that you have 2 versions of something you want to compare. And the way you compare them is by taking the subject population, in this case it's, say, the users of your website, and subjecting half of them to one of the variations and half of them to the other variation. So here, maybe you want to compare using a black buy now button against a red buy now button. And so you randomize and send half of your users here and half of your users here. And then ask yourself some questions like, which one has a higher conversion rate? Okay? So A/B testing is basically the process of running experiments. And the only reason that phrase matters is that that's the phrase that's used in the tech industry. Otherwise, this should really be a talk that's called randomized controlled trials. Now, one of the themes of the talk is going to be that running A/B tests in sort of the tech industry changes how we think about randomized experimentation. Okay, and I want to get to that. But for now, I just want to make sure that we set context, set what we're talking about. It's basically that the prototypical type of experiment is going to be something like that. Okay, A/B tests are used for everything. So they're used to test out algorithms like search algorithms, or Uber and Lyft will test out pricing algorithms using A/B testing. They're certainly used for changes to design. In more sort of interesting ways, they'll often be used to test out even things like logistics. So like on the back end for Amazon or companies like that, how they handle delivery. Okay. So let's start 100 years ago, well before HCI. And what we're going to think about is the origins of A/B testing. And kind of a remarkable fact is that most of the statistics that are displayed in A/B testing dashboards today in tech companies actually rely on things that were done 100 years ago. So Farmer Ron, and Farmer Ron here is Ron Fisher, who's sort of the father of the way we think about experimental design. He's a very well-known statistician. So what does he want to do? So he wants to test 2 fertilizers. Okay, and this example, the reason it's about fertilizers and crop yields, is this really was like the original motivation for thinking about experimental design. Sorry, Michael, I should have said that before you ran up. So what does he do? So the way you are taught, if you take a Stats 101 class or you read a experimental design book, the way you're taught to do this experiment is to apply what's called fixed sample size testing. Okay, and I'm going to walk you through how it works. And again, just to reemphasize, right? I am doing things from first principles, so my apologies if this is sort of old hat to many of you. But hopefully, for those of you for whom it's not, this just sets context correctly. So the first thing you need to do is you need to commit to your sample size, which is how many plots are you going to use to compare these fertilizers. Okay? Obviously, the more plots you use, the more likely you are to get kind of an honest assessment of whether one is better than the other. So higher sample size will be better. Okay, then what do? You wait for a crop cycle, and you collect your data at the end. So you use one fertilizer in some subset of the plots, another fertilizer in the other subset of the plots, and then you wait until the end and see what you get. And here's the key part. The way that you analyze the data is by running the following literally hypothesis test, which is that I hypothesize what would have happened if there really was no difference between the two fertilizers, right? So I had a collection of plots of land where I used one fertilizer, another one where I used the other. And what I first asked myself is, suppose there really was no difference between these two, right? What do I think would happen in that case? Why do I run that hypothesis test? I compare it against what I actually received. And now the question I ask is, well, how unlikely is it that if there really was no difference, that I would see what I got in my experiment? Okay? That's what's called the p-value. So the p-value is literally a measure of false positives, because it's basically saying that, if there really is no difference, and you believe that you look at the data, and what you conclude is that the data is really unlikely if there had been no difference, you could still be wrong. There still might have been no difference. And it's just that rare thing that happens where even though there was no difference, you actually see a big difference, right? So that event where you think there's a difference and there wasn't one is a false positive, right? So the p-value is a way of capturing the false positive probability. And the role that it plays in decision making is that you set for yourself a tolerance level for false positives, all right? That's often called the size of the test. What you decide for yourself, well, what level of false positives are you willing to tolerate? In scientific publishing, we typically want p-values that are smaller than 0.1%. In industry, you'll see people make decisions where the cutoffs are like 5% or 10%. In some cases, false positives matter a lot. In some cases, they matter little. Right? And that's kind of a measure of risk that you're willing to tolerate. You should really think of that in the same way that you would think about binary classification. So in binary classification, you're trading off false positives and false negatives. The trade-off is that as you become more conservative here, you're also less likely to detect things that are real. Okay? And so that's essentially a measure that trades off for you. Are you actually going to detect real effects against kind of making mistakes and claiming that there's a difference when there really wasn't one? Right? And so what Farmer-Ron does then is he cuts off the p-value at 5%. And if it's less, then he says his results are significant. Does this make sense? I want to stop here for a second and ask if there's any questions on what Farmer-Ron is doing. So again, the key idea behind Farmer-Ron's approach is this idea of theorizing about what might have happened if there was no difference. And then asking, well, how likely or unlikely is it that I would see what I got in the experiment that I ran? Okay? Right, okay. So this is very classical. I should add, by the way, that process of theorizing about what you might have received if there was no difference, that's typically what's referred to as frequentist hypothesis testing. So when you hear the word frequentist, it refers exactly to that kind of theorization about what other things might have happened. Okay. So there's an important point about this approach. It's not just like one way to think about things. It's actually, in some sense, an optimal way to think about things. All right? And I won't quantify in what sense it's optimal. But informally, what happens is that if you do this, right, then under some assumptions, lots of stuff being brushed under the rug there, this approach actually allows you to optimally trade off false positives and detection of true positives. So in particular, when you work in binary classification, when you're building a classifier, you can ask yourself, you look at the ROC curve, and you're looking for curves that trade off false positives and false negatives as well as possible, right? So one way to think about this approach as a binary classification approach, where your goal is when there really is a difference to detect it, and when there's really no difference to not say there's a difference, right? So you're trading off false positives and false negatives. This approach actually achieves an optimal trade-off there. Okay, in an appropriate sense. So that's one of the reasons why it survived for 100 years. It has this optimality property. And it has this optimality property despite what I would call a relatively simple user interface. The thing about this rule is that you don't actually need to be a statistician to apply that rule. If somebody else runs the experiment, they compute the p-value, they throw it up on a dashboard, all you have to do is decide what level of false positives are you willing to tolerate. And that's not an unreasonable decision to be able to make, right? To ask yourself, well, how bad would it be if we made this call wrong? On some things, it would be quite bad. On other things, not so bad. And I can tailor that 5% accordingly. But other than that, that's the only thing I need. And then my user interface is really simple. Just cut the p-value off at 5%. Okay? So this is I think one of the reasons why it's survived for so long is because it's optimal despite a simple user interface. I think one other thing I want to highlight about this is that this also has a really nice organizational benefit in companies. Because in companies, you'll have many different people processing the same dashboard of results, right? And one nice thing about this is that a single number, the p-value, summarizes the experiment. And each person can then bring their own desired sort of risk tolerance to the table, which is this false positive probability, and cut the p-value off and draw their own inferences. So that's sort of another nice feature of this, is that you've got a kind of portable description of the experiment that can be shared across many people that might have different desired false positive probabilities that they actually care about. Managers versus data scientists, for example. OK? Any questions on this? Pause for a second here. All right? Yeah. Oh, no, good? OK. All right. OK, so now let's flash forward 100 years. And I think this is actually going to say 2016 because the slides are a little bit out of date, but that's fine. So in 1916, data was expensive and slow. Practitioners were trained statisticians. And this is a really important point. I think one of the points I want to emphasize is that 100 years ago, if you're using this methodology, you could be pretty confident that the person you're showing the p-value to was also a statistician or a scientist, that they understood where the p-value came from. Okay, and they understood how to process it. They understood how to think about it, the way I just told you on the previous slide. This is Ronald Fisher, the statistician that I mentioned. But in 2016, we live in a really different environment as far as experimentation is concerned. Data is not expensive and slow. You don't have to wait for crops to come in after a full season. You get data in real time, right? And not only do you get the data in real time, it can be processed and visualized and displayed to the user in real time. And not only is this happening, but at the same time, the people that are looking at these dashboards, I mean, it could be anyone. It could be you. I mean, many of you are going to get jobs where at some point in the next 5 years, you're going to look at a dashboard that contains the output of an experiment. Okay? And that is a huge change from where we were 100 years ago. We're not necessarily expecting that every person that's going to look at the output of an experiment is someone who is a trained statistician anymore. And I guess one of the things we want to understand is, like, what are the consequences of that shift? So let's ask, how are you different from Farmer Ron, right? So here's how you're different. And in the background there is a data center. So the first thing is that if you're a data scientist staring at this dashboard, then time is money. So you want results as quickly as possible. Okay, so there's this trade-off to you. See, the thing is, when the data only arrived at the end of a crop season, yeah, you might want results earlier, but you don't really have a choice. You have to wait till the crops grow. But that's not a problem in a tech platform. Because now the data is coming in continuously, and it's more reasonable to ask yourself to sort of stop the test as soon as possible. One of my favorite questions in industry is, how long do I have to wait to get statistical significance? That is like the most commonly asked question of a product manager is, just how long are they going to have to wait until the test is done? Okay, so that's one. And as a result, what you end up doing is that you've got this dashboard up that's tracking the experiment for you, and I'll show you an example in a second. So what do? You just, every day when you walk into work, you pop it up. Because every day you're wondering, is this the day that I can stop the experiment? Right? Like, do I have enough now? Have I seen enough? All right, that seems reasonable, right? You're living in a real-time data environment, so it seems reasonable. And what you do is you rely on that dashboard to tell you when your results are significant. Okay? So this is what's called, so the thing Farmer Ron is doing is what's called fixed sample size testing. A crucial feature is that Farmer Ron committed to the sample size that he was going to use in advance, in particular the time of the experiment that he's going to use in advance and the number of samples he's going to use in advance. What you're going to do, though, is adjust the test length in real time, which really means you're adjusting the number of observations you're getting in real time. All right? You're going to look at the data to decide how long this experiment is going to be, which is not what the textbook tells you to do. It's not what Stats 101 advises you to do. All right? And you're kind of in uncharted waters at that point. And so what you do is you adjust the test length in real time based on the data coming in. And notice, one of the reasons I set the slide up this way is I want to point out you're doing it for good reasons. Because you want results as quickly as possible. So it's not that you don't know your statistics necessarily. That might be part of the reason. But the main reason is just that you care about getting results as quickly as possible. So that's why you adjust in real time. Okay? So here's a sample of what these dashboards look like. This is what the Optimizely dashboard looked like just before we made the changeover to the new methods that we use. I want to point out that the methods that we use don't change the dashboard. A key feature of the methods was actually to leave the dashboard the same. What we're going to do is change the numbers that are in the dashboard. Right? But almost any company that you go to is going to have dashboards like this. And I want to just quickly run through what the components are. First of all, I want to point out that the biggest numbers in the dashboard are how long the test has been running. which really the reason that's there is to act as like this running timer that, every time you look at it reminds you that time is money and that you want to stop as quickly as you can. All right? Then over here what we have is basically a matrix where the rows are different variations of that, say, the web page that you're going to compare against the control web page. Right? So each of these gets compared back to the control. And then in the column, we have different metrics that we might care about. Views, an example click, a click on a picture. And then each of these boxes is telling us whether on that corresponding metric, that particular variation is better or worse than the original. Okay? And so what people are looking for, and the green and the red are the platform signaling statistical significance to you. So what people are looking for is to wait as little as possible to be able to get these things to the green and red answers that they want. And I guess the thing I love most about this dashboard is actually this phrase right here. I don't know if you can read it. It says, how long should I run my test? Okay? And the reason I love that is because Farmer Ron, from the textbook, knew that question needed to be asked before the dashboard got created. Like, that was the question you were supposed to answer before you ran the experiment. I love the fact that this is a question that's being asked while you're running the experiment. It's on the results page, not on the project design page, okay? Which is a complete inversion of how experimental design was supposed to work. So we're actually encouraging you to think in real time about how long to run the test, okay? So here's a thought experiment. Suppose that 100 of you are now in this position of running experiments. There's about, I don't know, probably 50 or 60 of you in the room. Suppose there's 100 of you, and you're going to run experiments like this, and you're going to follow a pretty simple rule. You're going to stare at that dashboard, and you're just going to wait until the first time the p-value is less than a fixed cutoff, say 5%. Okay? But the experiments that you're running are interesting in an important way. They're not actual A/B tests. They're what are called AA tests, where both of the variations are actually the same thing, and you know that. All right? So this would be the case where both buttons were black. And why are you doing this? I'll come back to that in a second. Well, let's suppose you do that, where both variations are the same. Okay, so the p-value is being cut off at 5%, right? Now remember, 5% is the false positive probability. Okay? So what are we expecting will happen if we follow a correct statistical procedure? What we would expect is that if we use a false positive threshold of 5%, any time we declare that there's actually a difference in an AA test, that's a false positive, because there is no difference. So how many of these should we declare a difference in? Probably about 5. Maybe a little more, maybe a little less. There's some randomness, but about 5, right? That's what we should get. So my question is, how many actually find a significant result and stop early with this rule of stopping the first time you see something less than 5%? And let's suppose that the sample size is up to a maximum of 10,000 visitors. What's the number that you get? Yeah, so it is a number higher than 5. That's right. Otherwise, this talk would end really quickly, actually. So what is that? Any guesses as to how big it's going to be? Yeah.
Everyone?
Everyone? Okay, that's really high, but it's lower than that. So it's not everybody. It's not quite that bad. I mean, actually, ironically, if that was true, right? I mean, as you know, a classifier that's always wrong is as useful as a classifier that's always right. So if we ended up in that position, we might actually have a pretty good rule. Just do the opposite of whatever the test says. But no, so it's not going to be that bad. Any other guesses? How many people think it's going to be above 10%? Okay, we'll run an ascending auction here. How many people think it's going to be above 20%? Above 30%? Above 40%? Above 50%? Okay, so it's above 50%. All right? So the number of people who stop early and declare there's a difference is actually over half. Just think about that for a second, all right? Now here's this procedure that I declared to be optimal and great and 100 years old and used repeatedly and all of that. And just a small amount of misuse, which is this monitoring of the test continuously and then stopping early, is enough to completely destroy the usefulness of this process. This is worse than actually experimenting, in my opinion, right? I think you'd be better off applying your own knowledge to your business instead of running experiments in this case. I've actually said that to people, that if this is what you're going to do, then just don't bother A/B testing, right? Okay, so the point is that in A/B testing, peaking, and it's not just the peaking, obviously, right? If you just look, it's not like that changes anything. The problem is the peaking and then deciding whether or not to continue the experiment on the basis of what you see. can dramatically inflate false positives, right? And I want to try to help you develop some intuition for why this happens. It's not obvious at all that this should happen, and I want to give you some intuition for that. Before I do that, let's just dig in a little into those numbers. How bad can it be? So what I'm plotting here is the false positive probability that you would obtain once the p-value is less than, if you follow this rule of stopping the first time the p-value is below a cutoff. Okay, does it make sense to everyone? Like I'm watching the experiment unfold, wait for the first time the p-value is below a fixed cutoff. So I'm plotting 3 curves here for alpha being 0.01, 0.05, or 0.10, so 1%, 5%, 10%. And this is the curve we were just talking about a second ago, the 5% curve. So at 10,000 observations, if you allow the experiments in principle to run out to that far, then 60% of them are going to end up with early stopping, okay? About 60%. And then even at 0.01, we're expecting 1% false positives. You have over a 20-fold inflation in the number of false positives, right? Okay, so let me first talk a little bit about why this is happening, right? And again, if this is something that you're familiar with, I apologize, but I think it'll be worth kind of just spending a couple minutes on it. So here's a graph of 1 minus the p-value, what's sometimes called the statistical significance or the confidence level, okay, in some of these dashboards. Which means here what you should be thinking is when the graph is high, then the p-value is low, right? And in particular, that red line there is like the p equals 5% cutoff. So above that is like 95% significance. So this is like the 0.95 line right here, okay? And what you're watching is the trajectory of 1 minus the p-value over time. Now the rule of stop the first time the p-value crosses 5% goes below is equivalent to stop the first time this graph goes above the red line. Okay? This is an actual graph that was in the Optimizely dashboard. Still, a version of it is still there. And so that would mean you would stop right here, okay? And even if you were a little bit conservative, you would have an opportunity to stop again down here, potentially. Like maybe you want to wait a little longer. Now this is an AA test. Okay, so this is a test which, in fact, there's no difference between the two things. Right? And you can see that even this is crossing twice above that line. So let's first try to understand why this causes an inflation of false positives. Here's the basic issue. What fixed sample size testing says is that I commit in advance to how many visitors I'm going to wait for. And I guess the thing I want to point out to you here is the x-axis is real time, but for a second, just pretend it's visitors. All right? It's not that big of a difference, actually. So let's suppose that the commitment I made is that I'm going to run the test. In advance, I tell myself I'm going to run the test out to here. Now, the statement that I have a 5% false positive probability, okay, the validity of that statement comes from the fact that if I ran 100 AA tests from here all the way out to here and waited until this point, at most 5% of them would be above the red line. Right? Does that make sense? So a key condition in that is I'm only looking at this point in time. That makes no claims about what goes on in the middle. All right? So now suppose I take those 100 tests. Think of each of them as one of these trajectories laid out in front of you. And you just walk your way down the line, and in each one, wait for the first time it actually crosses the red line. So you're just cherry picking, right? In every single one, you allow yourself to stop the first time it crosses the red line. The point is that although only 5% of them are going to be above the red line if you had waited to here, in fact, 60 of them are above the red line at some point in this period of time. All right? That's the basic problem. So the problem is favorable selection of the sample path on the basis of what it's doing before you hit the terminal point. All right? And I think, so coming back to why AA tests are interesting, the reason I found this example so interesting, like Optimizely had data on AA tests. And the reason they had it is because customers would run AA tests as a way to check the platform. So basically, like, OK, let's say you sign up for an A/B testing service, something that's going to help you run experiments. And you're like, I don't know if this is actually going to do what I need. What's the first diagnostic test you could run? Run an experiment where you know what the answer is supposed to be, that the two things are the same. So naturally, when you run an experiment and the two things are supposed to be the same and you get significant results, what do? You call the customer support team. And you're like, wait a second, I ran this experiment, the two things are the same, what's going on? And I got to say, I really feel bad for the customer support team. There's no easy answer to this question. Like, one answer is that the customer is wrong, right? Because we gave you the right statistics, you just used them incorrectly. And that's not something you're going to tell someone on a customer support call. And the other obvious answer is we will look into it for you, which is ultimately what we did. But there's not a lot to look into. I mean, in the end, this is supposed to happen this amount of time. And there's not really a good answer to that, right? So, I think, so I already said all this. So basically, like the key point is that if you wait long enough, there's a high chance of an eventually inconclusive result looking significant along the way. Yeah?
So just echoing this in maybe terms that many of us have experienced, you have the Golden State Warriors playing the Lakers or something. There's the question of who wins the game, and maybe the Golden State Warriors win 95% of the time. But what this is saying is there any point in any of these games in which the Lakers were temporarily leading?
Yes.
And that happens a ton of the time.
That's right. Exactly. Yeah, that's a really good way to think about it, basically. That's right. There's a huge difference between asking whether the p-value is ever going to look significant along the way and whether it actually looks significant at that fixed point. Yeah. There's nothing about the design of Farmer Ron's method that's allowed to let you look at it continuously and know that you would still have validity. Yeah. Oh, sorry. Oh, sorry, Michael. You were going to say something else.
This is just very fast. If let's say we had picked 1 and we picked, halfway.
Yeah.
You would then still, and you waited there, you would still get the correct performance at that point, right? That maybe things are always moving around, but just so happens that only 5 of them would end up above the...
Yeah, for any fixed point in time, you're okay. And actually, you can get more sophisticated than that. You can ask questions like, suppose I only use 2 points in time. So look at the first and decide based on that whether to continue or not. And then look at the next one if I continued. And those are adjustments that have been made in things like clinical trials, where you'll stage the clinical trial, and then you'll run part of it, look to see what happened, and make a go, no-go decision on the next stage. And then it's easy to kind of back out from that. What are the right stopping rules to use and things like that. And at some level, actually, the methodology we use is really like a smoothed version of the stuff that's done there. So James, you had a question?
So does the platform give the person designing the experiment like a way to do a power analysis or something to make an estimate to say this is how many users or how long you should run the test?
Yeah, so that link that I pointed out on the dashboard, the how long should I run my test link, is actually a power calculator. It's basically a sample size calculator. And I think, again, the consideration there is that test is supposed to be, that calculator is supposed to be run before you run the experiment. Now, you raise an interesting point. So when I talk to people in industry about this, like one common response is to do the following, which is to run the test, and then while you're running the test, you apply the following 2-stage rule. The first thing you do is you wait to see is the p-value below 0.05. And okay, if it's not, you definitely don't stop. But let's suppose it is. Now you apply a secondary diagnostic. And the secondary diagnostic is to take what you've observed, the current effect that you're observing, the current difference, and run this sample size calculation using the current difference as the difference you're trying to detect. And then that'll spit out how many samples you're supposed to wait for. And as long as you've waited at least that many samples, then you stop the test. And it turns out, so that's what's called a post hoc power calculation. That has exactly the same issue. It's going to lead to exactly the same inflation, kind of inflation.
But isn't even showing the p-value wrong from the perspective of how these statistics were designed?
Absolutely.
And so it shouldn't be showing it. It could show you, yes, that's 10% better, that's better, but it should be saying, you need to do this many more people.
Yeah, actually, okay.
Approximately, and we're not going to say what the p-value is until you reach there or some stopping condition.
And that's a great point. So hold that thought for a sec. I'll come back to that in a minute. Yeah.
Would it be valid for someone looking at this graph to ask themselves, all right, what percentage of the time am I above that p-value line, and use that to get a method, like an idea of the significance of these results?
Yeah, I mean, definitely. So I'll talk to you a little bit as we go along. I'm hoping to be able to spend at least 10 minutes just to give you some of a peek inside the methodology. And roughly speaking, I mean, that's the idea. Like, if you want to make it possible for people to continuously monitor, you have to understand something about how frequently these kinds of fluctuations can occur. And then you have to control for that. So I think at some technical level, I think what you're describing is roughly the approach that has to be taken. And I'll try to formalize it.
Why don't you stick the customer support into the program?
So expand.
So anticipate the question. You know what I mean?
Yeah. Okay. So all right. Since I love this audience, there's so many suggestions of how to solve this problem, right? And so let me first frame the problem correctly, because this is the problem we tried to solve, and then we'll talk about some potential solutions. So what would the user like, first of all? I want to just be precise about this, because again, I want to emphasize that they're not doing something entirely stupid. They actually have a good reason for looking at the tests early. And the thing the user would really like is they would like to be able to choose when to stop adaptively. Adaptively meaning as they're watching the data. And the reason is because they really want to trade off the sample size against detection of true positives. If it feels to them like you're not going to likely detect something here, they would love to be able to stop sooner because there's an opportunity cost to not doing other stuff, not running other tests with your site, right? And what they would love is then, at that point, to use this simple rule that if the p-value is small enough, the result is declared significant. So fixed sample size testing is really nice because it optimally balances false positives and true positives, but it's not adaptive. On the other hand, adaptive testing, while meeting the first goal, is something which massively inflates false positives if we use the same p-values, right? And so when I was confronted with this, the first thing I did was talk to my colleagues here, and I asked, OK, what should we do? So the first suggestion was, in a safe for kids version, abbreviated as the RTFM approach. And that was, well, basically, and I guess at some level, this is what, one version of putting support into the platform would be, to just tell people, here's how you run a fixed horizon experiment. A more extreme version would be what James suggested. We actually don't even allow them to look at the p-value until the horizon. Right? And there's definitely some companies that run their tests this way, where it's not even possible, you're not allowed to look at the p-value or reject or anything like that before some fixed horizon run length that you've committed to. Okay? So that's definitely one solution. And this is a convenient solution because it allows us to basically say, our methodology was right. You just don't know what you're doing as the user. And therefore, the right fix is to fix the user. Okay? Now, I'm in an HCI seminar, so I hope you can guess what the next thing is that I'm going to say, which is that, I think it's very hard. It's very hard to envision a scenario where you change the user. So our approach was to start by presuming that there had to be some reason why they're doing what they're doing. And like I said, they have this opportunity cost to waiting too long. And instead, the goal is to commit to this as a constraint. Right? It's not stupid of them. The data is coming in real time. So if you just think about it from the perspective of the range of things you could possibly do, shouldn't you only be able to do better if you're taking advantage of the data as it's coming in? Right? It's a weird constraint to impose that I refuse to look at the data as it's coming in. So the question isn't so much to read the textbook necessarily, but rather, can we allow them to be adaptive and still give reasonable inference and reasonable control? Okay, so we actually committed to this as a constraint, and then said, can we design a procedure that does a good job relative to that constraint? Okay? And so the approach basically that we took was to change the p-value. So kept everything else the same, but we changed the notion of significance. And how do we change it? And this is what I'll dig into a little bit with you to show you what we did. We allow users to continuously monitor the test. So that's the commitment to that constraint. They can be adaptive. And then we report what we call an always valid p-value. So this is something where no matter how the user chooses to stop the test, there will be no more than a 5% false positive probability. And in a moment, I'll walk you through, like I said on the board, kind of the basic idea behind how that works. The method that we used, and I won't be able to talk about all the technical results related to this, but I'm happy to dig into this more with anyone here. I'm at Stanford, obviously, so you can catch me anytime. But the key results behind our approach are that we're able to provide a nearly optimal balance between test length and detection of true positives, while controlling false positives, the way we said here, and allowing the user to be adaptive. So sort of the way we think about it is that we're trying to recover something which is giving kind of a good balance between sample size and detection to the user, while controlling false positive probability, and most importantly, allowing them to be adaptive, all through the same type of user interface that they're used to, which is this p-value being reported in the dashboard. Okay? I think there's a longer conversation about whether p-values are a good idea for this kind of stuff, and I think I'm happy to have those conversations as well as those of you at lunch know. But at least let me tell you a little bit about how this works. All right? So I'm going to actually pause here on the slides and move to the board, but before I do, let me just ask if there's any questions or more comments. I guess probably the biggest question is yeah, so what did you do, right? And I'll try to explain that a little bit. Okay? All right, so could you raise the screen and then turn the lights back on? Do I wave, Michael? Oh, there we go. Michael said wave, and the screen would magically go up. Awesome, thank you. And if there's lights here, that'd be great to put them back on the board. Oh, can you raise it up? You can turn the screen off entirely, actually. And just raise it up so I can use the board. Let's see. I think I can start here, but it would be nicer if the screen was gone. Thank you. And let me just pull this out. OK. So here's the basic idea. All right? I'm going to just look at a very, very simple example for a second. So this requires a little bit of suspension of disbelief on your part, but hopefully you'll bear with me, all right? Which is, I want you to imagine that I'm giving you a collection of values, say x0, x1, x2. These are all independent values that come from a normal distribution, all right, that has a mean, let's call the mean m, and a variance of 1. Okay? And the only thing I'm going to assume is that my goal is to use the data to figure out what the mean was. So like just intuitively, right, like thinking about the law of large numbers and things like that, what I'd expect, of course, is that if I take the sample average of these things, that's going to about look like the mean. And the more of them I have, the closer it's going to be to the mean. Right? So that's how I would guess what the mean is. The natural thing to do is to stare at the sample average. The more of them I get, I know it's getting to the mean. I actually know a bit more than that. Right? We have the central limit theorem. And the central limit theorem basically tells us that not only is this thing going to look like the mean eventually, but if you ask what's the variance of the sample average, or like what's the standard error, this is hopefully something that you might have seen before. The standard error is proportional to 1 over the square root of the number of samples that I have. So that's like the spread in my estimate. Okay? So the way I think about getting a good estimate is the way I pick my sample size, I pick my sample size n so that 1 over square root of n is about the tolerance that I'm willing to accept in my estimate of the mean. Does that make sense? Okay? All right, so now let's just do all our analysis in sample mean world. So what I'm going to do is I'm going to plot for you kind of what's happening over time. Let's make that n, sorry. So that's a number of samples that you have. Okay? And what you're going to do on this graph is visualize a sample path that depicts the sample mean. Okay? Now what I'm going to do is I'm going to ask myself that the equivalent of testing whether there's a difference between the two A and B cells in this simple setup is going to be to try to figure out whether m is different from 0 or not. Okay? So if m is not different from 0, which m is actually 0, but I declare it to be different from 0, that's a false positive. My goal is to control those. If m is different from 0, and I fail to note that, then that's a false negative. And I want to control that too. I want to do a good job on both sides. Okay? So when you're thinking about what the sample mean is going to be doing over my samples, if m is actually 0, you should visualize something which is swinging all over the place, but where the range of the swings is about 1 over square root of n. Okay? And then as I get down to infinity, it's going to converge into 0. If the sample mean is different from 0, I'm going to get the same kinds of swings, but away from 0. And eventually, it'll converge into what the right value is. So here's the problem. The problem is that when I claim that I will stop the first time that the p-value is below 0.05, like using the classical Farmer-Ron p-value, that is equivalent to stopping the first time that the sample mean crosses a boundary that looks like it's proportional to 1 over square root of n. So I'm just going to draw down 1 over square root of n here. Okay? And so this boundary looks like a constant divided by the square root of n. And the same thing, this is minus the same constant divided by square root of n. So when you're watching your sample mean, so that the equivalent of waiting for that AA test to go above the red line is waiting for the first time your sample mean crosses these dashed lines and saying, I'll stop now. Okay? So the problem is that there's a resultant probability that tells us that this line is going to get crossed infinitely often by the sample mean. Okay? Not just once, but infinitely, under the assumption that the true mean was 0. All right? It's obviously going to get crossed if the true mean is non-zero, right? Because if the true mean is non-zero, eventually I converge to the true mean, that's definitely going to cross one of these two dashed lines, all right, whether it's negative or positive. But if the true mean is 0, it's not obvious that it's going to cross these two dashed lines, right? The limit will actually lie on this line. Okay? But it turns out that there's a resultant probability that says you're actually going to cross this infinitely often. So you're guaranteed to make a mistake if you were to wait indefinitely. So you know that 50% or 60% that we were talking about when I did the survey? That would be 100% if I allowed you to wait as long as you wanted. You'd be guaranteed to cross. Okay? And again, you'd be guaranteed to cross again and again. So even waiting for multiple crosses would not save you. So what you have to do is you have to fundamentally just be a lot more conservative in this boundary. So 1 over square root of n is not good enough. In fact, the result says something stronger. It's not just that 1 over square root of n will be crossed infinitely often. It's that square root of log n over n is going to get crossed infinitely often, all right, which is a boundary that lives above this one. So in fact, the first boundary, where I can guarantee that I only cross with some fixed probability that's not 1, is something that looks like square root of log n over log n over n. Okay? And so if I could draw the picture in to make it more visual, basically what I mean is there's some other curve that looks like this. And what these define, sorry, that should tilt back down. It goes towards 0. Okay. So these curves also have the property that they eventually converge down to 0. Square root of log n over n goes to 0 as n goes to infinity. But they have the property that if the truth is that m is 0, and you watch the sample mean, the probability that it crosses one of these two black lines, the outside black lines, is actually strictly less than 1. And by tuning the constant in front of this, so there's another constant, let me call it, it's different constant tilde times that. Tuning this constant, which basically involves moving this in and out a little bit, I can actually adjust what that probability is. Now, what is that probability? That's my false positive probability, right? So what we do is we basically pick the constant here so that the probability that you ever cross the black lines is bounded at exactly what your desired false positive control is. Okay? So that's the thing that gets you the false positive control, is to shift the boundary out. The reason this is the thing we use, like, why don't we just use something where the boundary is flat? Like just like that, right? That would ensure that at least I would have false positive control. The reason we don't do that is because then if the truth is different from 0, I'll never cross that boundary. Or there's a good chance I won't. In that case, I won't detect real effects, right? So this boundary is still nice because it still goes to 0 as n goes to infinity, which means if the truth is different from 0, remember the sample mean is gonna center around that the truth that's different from 0, I'll eventually cross this black boundary. So I'm guaranteed to cross if the truth is different from 0, and I can control how frequently I cross if the truth is equal to 0. Yeah?
Doesn't this assume that I know the standard deviation? So that if I don't know the standard deviation that I'm sampling from, like, I don't know exactly how wide out these things are.
Yeah, I think there's a lot of really good questions there. So there's some assumptions about what the variance is in here that are important.
So like if I'm running an A/B test, for example, I don't know how much variation there's
Yeah,
going to be.
I think that's right. So I guess, so there are a couple different things I have to say about that. I think if you were to translate from this to the A/B testing framework, right? One is the issue that the variance might not be known. The other is, of course, the issue is that this is not even an A/B test. It's just an A test. So I need two cells, and then I have to ask, well, how does this change when I'm actually tracking the difference in conversion rates of two groups? I guess in the interest of time, let me just say that that's where some of the technical work goes, to actually generalize this approach into a setting where those are some of the things we're dealing with. The particular issue of variance is actually not the most difficult one to deal with. There are a couple other issues that prove to be more problematic. Let me defer that for a moment, so I can kind of keep just make sure I get through a few other key points I wanted to make. So I know that this sounds a bit technical, right? So let me zoom it out again and kind of summarize what the key idea is here. So you give me, and I'll move these two boards up. So we're gonna, on the next two boards, I'm gonna write in a slightly less technical way what the basic idea is behind what we do. All right? Okay, so the idea is that first, the user picks, I mean, they don't have to do this. They can do this on their own, but the user, let's say user has a desired false positive probability target alpha. All right? And then what we do is we say, OK, the rule, stop the first time the sample mean crosses constant times square root of log n over n can guarantee alpha if constant is chosen right. OK? And then if the truth is different from 0, this rule is guaranteed to detect it eventually. OK? So there are a couple more points I want to make. So this is kind of a summary, non-technical summary of what I set up here. And there are a couple more points I want to make. So the first one is, how do we get p-values out of this? OK, and the way we get p-values is that we think about, we give this time a name. OK, so let me call this time T alpha. So T alpha is exactly this time here. You fix alpha, and then it gives you what's the first time you would stop. What's the first time that this boundary gets crossed, okay, with the right constant being chosen based on alpha. So the rule we give is that the p-value at any given n is the lowest alpha such that T alpha was before n. You've got a family of these right now, right? So for every alpha, there's one T alpha. And some of them have not happened yet. Some of them, given the data you have so far, you wouldn't stop. So and of course, they're nested, right? You're going to become more conservative when alpha gets smaller. So what you can do is you can say, all right, given where I am right now, what is the smallest alpha at which I would have stopped by now? Okay? And that's the p-value. That's the p-value we display.
In practice, you just calculate this out from 0.01 to 0.99 and just show it.
In practice, actually, it turns out to be much simpler than that. There's a very simple static update that does it. You don't have to compute all the T alphas separately. You just compute one number, and it's enough. Yeah. So I think, as I mentioned, I had to suppress some of the technical details. So it turns out that maybe if I say one sentence about it, and so if you want to tune out for a second, the next 30 seconds or so are going to be slightly technical. The actual way we run the test is we compute a version of a likelihood ratio statistic between the alternative and the null. And then what you're looking for is just how large the likelihood ratio statistic is relative to 1 over alpha. And so you only need to track that one number, the likelihood ratio statistic. And then the smallest alpha is actually just, it is related only to that. So you don't need to compute all of them separately. Yeah. So that's the rough summary. OK, so I've got a bunch of these. So the p-value definition is the smallest alpha such that T alpha, so this is the p-value at time n, is the smallest alpha such that T alpha is less than or equal to n. And that's the p-value. This has two nice properties. So one is, now imagine that somebody stops the first time the p-value falls below alpha. What does that amount to? Stopping the first time the p-value falls below alpha is stopping at T alpha, by definition. OK? And as we said, T alpha is chosen so that you've guaranteed false positive probability alpha. So this is actually coming back to your way of thinking about things, of controlling these additional fluctuations. That's exactly how it's happening. We first work out what is the range of these fluctuations, and then we set T alpha up to make sure we've controlled them. And then now, if the user stops the first time this crosses alpha, it's exactly the same as controlling the fluctuations correctly. That's one point. The other point, though, that's nice is that it turns out that's not the only rule for which you would get false positive probability control. No matter when the user chooses to stop in an adaptive way, their false positive probability would be bounded by alpha. And that's an additional few lines of proof from here, that I'll skip for now. But that's kind of a nice thing about these p-values. So this is the nature of the always valid p-values that we use. I want to make one comment about the methodology. The procedural test that we use, this likelihood ratio statistic that I was mentioning to Michael, it's something called the mixture sequential probability ratio test. And it's not our idea. It's something that actually has been in the literature for a long time. So Herb Robbins, who is a statistician here and passed away, and David Sigmund, who's still a statistician here, developed kind of foundations of it. And then Zhe Lai, who's also a statistician here, kind of did a lot of work to build out some of the theory around it. And the statistic that we use, these T alphas that we construct, I guess picking the right constants here, comes from their calculations, some of the stuff that they did. OK? All right, so I want to show you a few more slides that kind of give you some sense of how this works, okay, and what's good about it. So let me wrap up with that. Okay. Okay. This is almost perfect, except for the fact that the screen's not there yet. Let's see. Try reloading one more time. All right, there we go. Second, let me try some more time. OK, so the last thing I want to talk to you about is, oh, sorry, go ahead. So T alpha is the first time that, so say you fix alpha. What that determines is the constant in front of the square root of log n over n. So T alpha is the first time at which you cross those two solid black lines with that particular constant in front of the square root of log n over n. So for each alpha, you get kind of one of these pairs of black lines. And of course, the more conservative you are, the further out the black lines go. Okay, so as alpha gets smaller, the black lines go out more. And so as alpha gets smaller, the T alphas get longer. It takes you longer to hit one of those two black lines. And the alpha is your false positive control, yeah, the 5% from our examples. Okay. All right, so let me wrap up with one last comment. So the test looks good because it's giving you two things. It's giving you a control of false positive probabilities, and it's giving you detection eventually. So the one problem with that is that it might give you detection eventually, but what if it takes forever to get there, right? And so one thing we wanted to do is we wanted to compare how we do relative to a test where you've committed to the fixed horizon run length in advance, okay? And so here's kind of how I would think about that. You have to give up something in return for continuous monitoring of the test. Even though you've got the data coming in continuously, you're now protecting yourself against a much wider range of things the user could potentially do, okay? And so here's the basic question. If the effect size is known in advance, meaning the actual gap between A and B is known in advance, in principle, you should be able to do only better by continuously monitoring, right? Because you've just expanded your feasible region of things you could do. With that knowledge, if you knew what the gap is supposed to be, then you can perfectly set up a rule to stop so that you do better. In practice, the problem is that you don't know the effect size in advance, and the test that we designed does not assume any knowledge of the effect size. And so what we want to do is we want to compare how we do against the fixed horizon test using data from Optimizely. Okay, so this is kind of a graph that takes some time to process, so let me walk you through it. So first of all, there's 4 tiers that when we launched this at Optimizely, bronze, silver, gold, and platinum, roughly ordered in terms of the number of customers they would have in experiments that they ran. Actually, what you were doing is paying for the amount of visitors running through Optimizely that you would use per month. So what am I plotting here? So I'm plotting a ratio of how long our test takes against how long a fixed horizon test takes. Now, for what? The for what is that I use a sample size calculator to determine a sample size under the following assumptions. That I know what the effect size is, that I have a particular false positive probability I'm trying to hit, and I have a particular false negative probability I'm trying to hit. Once I fix those 3 things, that determines the sample size on a fixed horizon test I need to be able to meet those constraints. Okay? So the first thing we do is we imagine, we took about 10,000 historical experiments from Optimizely that had run long enough that you could kind of treat the final effect as like the true effect size. And we use that in the sample size calculator to work out how long you would run a fixed horizon test. That's the denominator. The numerator is that we used our testing procedure on top of the same data and asked, OK, when would you stop? When's the first time the p-value would cross the cutoff? So the first graph I want to point you to is the solid black lines, which don't look particularly good. So these ratios, remember, it's a ratio of ours to the fixed horizon testing. It looks like it can range as high as 3. So that'd be like a 3x inflation in the run length of the test, okay? Which sounds terrible. But that 3x inflation presumes that you perfectly knew in advance what the actual effect was going to be. Right, now suppose that you calculated a sample size assuming something about what the effect is going to be, but you got the effect wrong. So you were off by 30% or 50%, which is not unreasonable. If you're looking for like a 1% conversion rate difference, being off by, oops, I forgot to turn caffeine on. Being off by a 1% conversion rate difference would amount to basically, would amount to having, a true effect size, which is a 0.5% difference instead of a 1% difference. So that's not unreasonable in practice. And now you can see, like, let's look at the dashed line, or the dotted line here. That's a case where you're off by 50% on the effect size estimate. And now our run lengths are typically much shorter than the fixed horizon run length. So this diagram, for example, most of the weight of that histogram is less than 1. So our ratio is less than 1. We stop faster than the fixed horizon test. And the red line is really the one that I would draw most of your attention to, which basically says, now suppose that the effect size comes from a prior, which is the distribution of effects we've seen across Optimizely. And like compare the fixed horizon testing for that relative to the fixed horizon testing, relative to the adaptive sample size testing that we do. And what you find is that in general, you're stopping earlier. In particular, the mean of all these distributions is less than 1. Okay, so on average, you stop faster. Sometimes you still stop later, but on average, you stop faster. And here's the reason for this. So I'll leave you with this, which is that if you're wrong about the effect, detecting an effect of size delta takes you a run length that's about 1 over delta squared. And the reason is that, this thing that I told you, that there's a 1 over square root of n uncertainty in your estimate. Right? So if you're trying to detect something that looks like delta and you have a 1 over square root of n uncertainty, you need about 1 over delta squared samples to resolve that uncertainty. Right? So the penalty for guessing wrong about, this should be a capital delta, sorry. The penalty for guessing wrong about this is really high. Being off by a little bit, like an effect size that's 2x too small actually takes 4x too long. So it's a huge, huge mistake when you're even slightly off about the effect. And our test, because it's adaptive, automatically kind of adapts to that. Right? So I'm going to stop there. There's a bunch of stuff on multiple testing that I didn't plan to cover today. But I just want to leave with this note, which is what I really love about this kind of work is the user is like a fundamental component of the modeling. And there's a bunch of other things I'm thinking about that are kind of like this, where I really think we have a lot of work to do on the methodological side to develop ways of presenting statistics to users that can actually lead to good decision making within the context of what feels reasonable and plausible to them. And I think you guys can think about similar examples of this all over data science as it's currently practiced. I found it fascinating because you've got these like relatively sophisticated tools being applied, and just a small amount of misuse can completely destroy their validity. So that's not the only case where that's happening, and I think it's incumbent on all of us, both in HCI and in kind of more on the statistical side of things, to do a better job of helping people make good decisions from the data they have. So I'll stop there. Thank you. Yeah, go for it. Okay. I guess I'll leave this up. Yeah.
Let's jump over to the humanities and sciences and social sciences side of campus, where everyone's going, replication crisis and psychology, yeah. Right? Can you
just
fix
like
this?
Or
on blogs, the equivalent.
Yeah.
Can we fix that through something like what you're doing? Like, as you're describing this, I'm remembering when I was doing undergrad research. I would talk to friends who were also spending the summer doing like psych research, and they'd say like, "Oh man, we almost had it statistically significant, but then it like swung away, so we're going to get some. There's no need to up our end." Like in theory, everyone does a power analysis, and it's like, okay, so we need 100 people, and then they do that. But in practice, if it's like 0.06,
you keep running.
You keep running.
Yeah.
And like it seems like
it's basically exactly.
It's the same problem.
Yeah.
So, and I'm wondering if we should just not be doing this just for A/B testing online, but instead do this for like my Chi papers and everything else that we sort of like now we assume not exactly the worst of human beings, but that like we're sort of greedy.
Yeah, so I actually have a few different comments I want to make about what you just asked. The first one is, you might have heard the term p-value hacking, and it's often brought up in the same sentence with replication crisis. And it's basically that like p-value hacking means p-values mean one thing, but people will pull all kinds of tricks to try to get significant results, right? And so the first thing I wanted to point out is that, I'm completely comfortable with some of the criticism of p-values. But one thing I worry about is that it's putting all the burden of failure on the statistic instead of something about the user model, right? And so that's one thing, is that I think like embedded in your question is that part of the problem is how people interact with p-values and what they use them for, and then how we interpret the consequences of that interaction. So second comment I'll make is that if you start applying this more broadly, I think there's some balance of James's kind of rules approach, where you like fix boundaries that people can't go past, and flexibility. And so like I think in psychology, in some of the journals anyway, you actually have to pre-file what your run length is going to be, what your experiment's going to look like, what are the confirmatory variables that you're exploring. Then you can do other stuff if you want, but all that stuff is set in stone now, and you can only manipulate it up to a certain point. And I guess the last point I'll make is that this is more just to make sure that all of you are curious enough to think about these things. This is one example of how looking at data that's coming in from an experiment can go wrong. Two others that I think everybody should know about, and those of you that took 226, I see Sam in the audience, so he knows this, is one is post-selection inference, which is basically an analog of that would be what you just brought up, Michael, where I first look at the results of the experiment, and then use what I learned to figure out which hypothesis test I'm going to report. Okay, so that's a major cause of the replication crisis. That's a form of p-value hacking. It's related to what we just talked about here. And then the other one is multiple hypothesis testing, which, as I noted, I didn't get a chance to talk about. But that's basically that when you run 100 hypothesis tests, if you have lots of variations, lots of metrics, you should expect 5 of them to be significant because you had a 5% false positive cutoff. And that's not useful inference, because now you're staring at a dashboard, your eyes are drawn to the green and the red, right? So what you need is something which helps people protect against the kind of human tendency to want to focus on the stuff that's significant in a world in which it's already known that some of those things are false positives.
So what does Optimizely think? Let's say you took 10,000 tests there. How do they go to sleep at night knowing that,
Well, we've implemented
a huge number of those are false positives?
No, so we actually implemented, in addition to what I talked about, we implemented control for multiple hypothesis testing. So if you run 10,000 hypothesis tests, your false discovery rate, which is the fraction of significant results that are false divided by the total number of significant results, would still be controlled at 5.
Across all of Optimizely?
It's not across all of Optimizely, it's across all each customer's experiment. Yeah, I see. That's an interesting question. Yeah, should we apply so? Yeah, I think that's a longer conversation. Should we apply FDR control across all of Optimizely? I think that's probably, that would lead to making no decisions whatsoever. But that's one way to control false positives, is to not make any decisions at all. Yeah. All right, should we stop there?
All right, let's thank
Okay,
Ramesh
thank
for
you.
spending this afternoon.
Great, so I'm really excited to be speaking here. It's my first time speaking to an HCI audience of any kind, so I hope you'll forgive me if I don't follow the norms that need to be followed. So a couple comments on the work I'm going to talk about. It is sort of work that has a pretty strongly statistical nature, but I prepared the talk sort of from first principles. So we're going to give, the talk is actually in 3 parts. There's going to be sort of an introduction to kind of what we did, and then I'm going to go at the board, actually, which is an amazing thing. I hope that everybody can be OK with that. So I'm going to actually use the board to give you some intuition for why our idea works. And then I'll go back and show you some more slides on some of the results and visuals of the platform. So what is the talk about? The talk is actually about some work that I did with a platform called Optimizely. And so I want to be clear that this is work that I actually did as a technical advisor to Optimizely. So, in particular, just by way of full disclosure, I'm still an advisor to them, and and this is work that I did essentially as a consultant for them. The idea was that who's sort of the father of the way we think about experimental design, is a very well-known statistician. So, what does he want to do? So he wants to test 2 fertilizers. Okay, and this example, the reason it's about fertilizers and crop yields, is this really was like the original motivation for thinking about experimental design. Sorry, Michael, I should have said that before you ran up. So what does he do? So the way you are taught, if you take a Stats 101 class or you read a experimental design book, the way you're taught to do this experiment is to apply what's called fixed sample size testing. Okay, and I'm going to walk you through how it works. And again, just to reemphasize, right? I am doing things from first principles, so my apologies if this is sort of old hat to many of you. But hopefully, for those of you for whom it's not, this just sets context correctly. So the first thing you need to do is you need to commit to your sample size, which is how many plots are you going to use to compare these fertilizers. Okay? Obviously, the more plots you use, the more likely you are to get kind of an honest assessment of whether one is better than the other. So higher sample size will be better. Okay, then what do? You wait for a crop cycle, and you collect your data at the experiments. And the only reason that phrase matters is that that's the phrase that's used in the tech industry. Otherwise, this should really be a talk that's called randomized controlled trials. Now, one of the themes of the talk is going to be that running A/B tests in sort of the tech industry changes how we think about randomized experimentation. Okay, and I want to get to that. set what we're talking about, it's basically the prototypical type of experiment is going to be something like that. Okay? A/B tests are used for everything. So they're used to test out algorithms like search algorithms, or Uber and Lyft will test out pricing algorithms using A/B testing. They're certainly used for changes to design. In more sort of interesting ways, they'll often be used to test out even things like logistics. So like on the back end for Amazon or companies like that, how they handle delivery. Okay. So let's start 100 years ago, well before HCI, and what we're going to think about is the origins of A/B testing. And kind of a remarkable fact is that most of the statistics that are displayed in A/B testing dashboards today in tech companies actually rely on things that were done 100 years ago. So Farmer Ron, and Farmer Ron here is Ron Fisher. We wanted to try to think about how people look at the information that you report after a randomized experiment called an A/B test in sort of technology platforms, and how do they process the information that they get back. Okay, so let's start by first just talking about what is A/B testing. So this is just to make sure that I set context for everyone. Hopefully those of you that have sort of been around the tech industry would have seen something like this before. But the idea is that A/B testing is, in Silicon Valley, we have to invent new names for old things all the time. So A/B testing is a new name for an old thing called a randomized controlled trial. Okay? And randomized controlled trials are sort of the gold standard of experimentation. The basic idea is that you have two versions of something you want to compare. And the way you compare them is by taking the subject population, in this case it's, say, the users of your website, and subjecting half of them to one of the variations and half of them to the other variation. So here, maybe you want to compare using a black buy now button against a red buy now button. And so you randomize and send half of your users here and half of your users here. And then ask yourself some questions like, which one has a higher conversion rate? Okay? So A/B testing is basically the process of running experiments. So you use one fertilizer in some subset of the plots, another fertilizer in the other subset of the plots, and then you wait until the end and see what you get. And here's the key part. The way that you analyze the data is by running the following literally hypothesis test, which is that I hypothesize what would have happened if there really was no difference between the two fertilizers, right? So I had a collection of plots of land where I used one fertilizer, another one where I used the other. And what I first ask myself is, suppose there really was no difference between these two, right? What do I think would happen in that case? Why do I run that hypothesis test? I compare it against what I actually received. And now the question I ask is, well, how unlikely is it that if there really was no difference, that I would see what I got in my experiment? Okay? That's what's called the p-value. So the p-value is literally a measure of false positives, because it's basically saying that if there really is no difference, and you believe that you look at the data and what you conclude is that the data is really unlikely if there had been no difference,